We'll start by installing DTrack to the local environment. This will install DTrack as well as TensorFlow and TensorFlow add-ons. We'll import DTrack under the abbreviation DT. We'll also import NumPy and Matplotlib, which are used for mathematical operations and plotting. Now we can begin the process of defining the data generation pipeline. We'll start by defining a particle. We will use a point particle, which is the simplest example of a particle. We'll give it a position of 0, 0 in units of pixels and an intensity of 1. To actually see the particle, we will have to image it through a microscope. As such, we define an image size as well as a fluorescence microscope. We also define the optical parameters of that microscope as well as the output size. We tell the microscope that we have just created to image the particle by calling it with the particle as the first parameter. Note that this creates an object which in turn creates images. It is not yet an image. To actually create the image, we need to call .resolve. We also show this image using Matplotlib. You can now see the particle as a bright spot in the top left corner. What we have created so far are 3 objects: the particle, the microscope, and their combination. These are examples of what we in DTrack call features. And since they are so important to working with DTrack, we'll explain them in a little bit more detail in another example. Here we have a notebook which explains features in a simpler but more abstract way. Here we had an add feature, which simply adds a value. But to what? Well, that is determined when it is executed. We execute it by calling the method .resolve. The first argument is then the input. So for example, if we execute the add1 feature on the input 10, we get 11. In a similar way, if we execute it on the input 9, we get 10. We can also change the argument of the add feature, for example to 5. We then get 10 plus 5 is 15. We can also execute 2 features in sequence using the plus operator. This means that the output of the first feature will be sent as the input of the second feature. For example, here we have one feature which adds the value 1 and a second feature which multiplies by 2. We can then combine these features into a single feature using the plus operator. This means that whatever input we pass will first have 1 added to it, and the result of that will be multiplied by 2. So for example, if we resolve this on the input 10, we get 22, because 10 plus 1 is 11, and 11 times 2 is 22. Similarly, if we change it to instead add 5, we get 30, because 10 plus 5 is 15, and 15 times 2 is 30. We can also execute a single feature multiple times using the power operator, or star star. Here we create the add1 feature, and we tell it to be executed 5 times. This gives 15, because 10 plus 1, 5 times, is 15. What is truly special about features is that any argument can be changed from a value to a function that returns a value. The simplest case here is simply a function that directly returns the same value. So passing a function that returns the value 1 is in fact completely equivalent to simply just passing the value 1. Where this becomes interesting is in the fact that you can have a non-deterministic output. For example, here we have defined an add feature which randomly adds either 0 or 1. So if we resolve this feature, we see that this time it added 0, because 10 plus 0 is 10. We can check that it was in fact 0 it added more explicitly by calling add 0 or 1 dot value, which is the name of the property, dot current value, which is 0. It is important to note that a feature will keep using the same current value until you call .update, at which point it will call the function again and use the new value. So for example, if we call add 0 or 1 .update and check the new current value, we will find that eventually it will switch to 1. Another important thing about features is that they store all the arguments they use on their output. So for example, if we execute add 0 or 1, the output contains a field called properties. From it, you can recover the current value of any argument that the feature used. So let's quickly look at result.properties. You can see that it is a list of dictionaries, where each dictionary corresponds to one feature which was used to create the image. For example, in the previous example where we had both add and multiply, each of them would have their own dictionary list. In the dictionary, you will see the name of the feature, which tells us that it was an add feature, as well as a value which was added to the image. You also have the hash key, which is not important for this example. This means that after you have created the image, you can go back and look at all of the arguments that were used in that specific image. We also provide the getProperty utility method. The first argument is the property you want to extract, in this case value. By default, getProperty only extracts the first instance of a property in the list that it encounters. You can change this to extract all properties in the list by setting get1 to false. Let's see how we can use this new knowledge in our original example. First off, we might consider looking into the position argument. For the network to be able to learn, it needs to see the particle in many different positions. So a natural choice would be to randomize the position of the particle. We can achieve this by calling np.random.round of 2. This returns 2 random values between 0 and 1, which we then multiply by the size of the image to get a uniform sampling of the position within the image. We combine the features, call resolve, and show the output. You can see that the particle was now randomly placed in the top right corner. Of course, we can choose any distribution for the position of the particle. For example, we can define it to be normally distributed around the center of the image. As we would expect, we now find that the particle is close to the center of the image. Let's go back and increase the standard deviation of the normal distribution a little bit. You will now find, as expected, that the particle is positioned close to the center of the image. You'll also find that even if we run the same cell multiple times, we get the same position. Recall that we have to call .update for the feature to grab a new position. As such, we'll call image particle .update. We'll resolve an output and show it. You'll now find that the position of the particle updates each time we run the cell. There are two main ways of adding more particles to the image, either using the plus operator or the power operator. First, we define a second particle, which is also a point particle, but the position is now uniformly distributed within the image. We add the previously defined particle with this new particle using the plus operator. This creates a single feature which resolves two particles. We then call the microscope with the two particles as the first input. We resolve an image and show it. we now see a single particle in the top right corner and another particle close to the center. The second way is using the power operator. Here we take particle 2 power 5. This means that we want to add 5 copies of particle 2 to the image. Note that each one of these copies will have its own value for its position. We call the microscope with the particles as usual. We remember to call update. We resolve an output and show it. We now see that we have added 5 individual particles to the image. In order to make the images more realistic, we also want to add noise. As such, we'll define 2 more features. One, which is the add feature, which simply adds a constant background, which can be seen as a background illumination, as well as Poisson distributed noise with a signal to noise ratio of 5. For the Poisson feature to determine the signal to noise ratio, it needs to know the background intensity of the image. However, the background is randomly added by the feature offset. In DeepTrack, we handle cases like these by determining a dependency between 2 features. In this case, we simply need to say that background is equal to offset.value, and can either be defined between 2 features or between 2 arguments within a feature. For example, you could then define the signal to noise ratio to be a function of the background intensity. We use the fluorescence microscope to image 5 copies of particle, to which we add offset and Poisson noise. We use the plus operator, which means that first the image of the particles is resolved. Then this is sent as an input to the offset feature, and the output of this is sent as an input to the Poisson noise feature. If we run this cell, we see that the image is indeed noisy and that the particles are close to the center. This is because we use the particle feature, which is normally distributed around the center of the image. We can change this to use particle 2, which is uniformly distributed within the image. We can now use what we learned about how arguments or properties are imprinted on the resulting image. We can call outputImage.getProperty with the key position and that we want more than 1. In this way, we get a list of the positions of all particles in the image. Let's quickly double check that these values correlate to the in-image positions of the particles that we see. We'll define a function that returns the in-image positions of the particles in the manner that we just described. We'll remember to update the feature, we'll then resolve it, extract the positions, show the results, and scatter the positions. The red crosses correlate perfectly with the particles' positions. This is a very powerful way to extract a ground truth label for the network to train on. There is also a second way to extract a label, which we will very briefly touch upon here. You can optionally pass keyword parameters to the method resolve. These override any arguments you've passed to individual features. For example, here we override the NA, or the numerical aperture. We first resolve an image with an NA of 0.8. Then we resolve the same image but with a NA of 0.4. As you can see, the second image has a much larger point spread function, as you would expect. With this syntax, you can, for example, train a network to remove noise, optical aberrations, or to repropagate particles to the focal plane. Now we are ready to define the neural network. DeepTrack is compatible with any deep learning library, but it is defined to be used with Keras. We also provide some standard architectures so you can get started quickly. Here we will use the convolutional architecture, which begins with a few convolutional layers and ends with a few fully connected ones. we define the input shape as image size, and that there's one feature channel. We also set the number and size of convolutional layers in a network. We specify that we want 2 outputs after the fully connected part, and we set the loss function to be mean absolute error. Finally, we also print a summary of the model. We see that the network consists of convolutional layers and max pooling layers, which downsample the image from 64 by 64 down to 32 by 32, and subsequently down to 16 by 16, 8 by 8, 4 by 4, and finally 2 by 2. This tensor is flattened into a 1024 element vector, which is then passed into a dense layer. And finally, a dense layer combines the results into a 2-element output. Now we are ready to combine all of our knowledge into a single data generation pipeline. We define a function that returns the position of a single particle and divides that by the size of the image. We also define a normalization feature which scales the input image to be exactly between 0 and 1. We use the fluorescence microscope to image a single particle. To this, we add offset, Poisson noise, and finally the normalization, all using the plus operator. We also need to define a data generator, which is how other packages can request images from DeepTrack. In this case, we'll use continuous generator, which is a very fast generator designed to create training data for neural networks. For the first 2 arguments, we'll pass the training set feature as well as the getPosition function that we just defined. We'll also set the size of each batch that the generator creates. Finally, we'll also need to define min data size, which is the minimum number of images that the generator will create before starting training, as well as max data size, which is the maximum number of images that the generator will hold in memory at any one point. It is usually a good idea to set the min data size to be at least 10 to 20 times the batch size, while the max data size is mostly bounded by the system memory. To train the network, we only need these 2 lines. With generator tells the generator that it is time to start creating images. The second line tells the model that it should start training using images from the generator and to train for 100 epochs. As this is just a Keras network, it accepts the same methods and arguments. It is finally time to start training the network. After just a few seconds, the generator has created enough images to start training, and the model is now being initialized. You can see the training being performed in real time, and it is pretty fast. You can also monitor the loss over time here on the right. I'll speed up the rest of the training. Now that the network has finished training, we can evaluate its performance on some unseen data. We extract a batch from the generator by calling generator of 0. From this, we extract the images and the position of the particle within each of those images. We'll also calculate a measured position by having the model predict on those images. We use a for loop to iterate through all of the images and extract the in-image measured position by multiplying the values by the size of the image. We do the same thing for the real positions. Finally, we show the images. We scatter the real positions using a cross and the measured positions using a circle. We see that the tracking is not yet absolutely perfect, but it is definitely getting there. A few more minutes of training should probably do the trick.